All right. So now that we've figured out how to translate concepts of dependence and influence, which are dyadic concepts, into a network level structure, let's actually look at 3 different ways this was done. So who'd like to take a shot at this one? Could somebody give us an overview of what's the main idea in this paper? How did they implement it? What's the key result?
I can try to give a summary.
Sure.
This paper talks about like what kind of organization structure can the organization adopt to balance between exploration and exploitation. So they come up with this semi-isolated. It means they are kind of separated, but then there are some person is connecting across different group. So they think this kind of group structure can help balance exploration versus exploitation, because this kind of parallel isolated learning within the subgroup enables exploration, and then there's also learning across different subgroups can enable the exploitation. So that's the main idea, I think. Yeah.
Okay, good. So let's try and break down the components of the model. So the model has basically a network structure of influence. In this case, the influence is the transmission of beliefs about good solutions. Right? That's what's happening. So each tie is essentially a channel for communicating beliefs about what are good solutions. And the channels have this pattern. And they start with the picture on the left, which is a nearly isolated caveman structure. So this is called Caveman Model because the story is that our caveman ancestors might have been like this, where within the cave, everybody is densely connected, but the links between caves are kind of sparse, right? So between any 2 caves, there's only one tie, right? And that gives you like a baseline level of ties in the system. So that number is fully determined by the number of actors and the cave size. So once you know the size of the cave and the number of actors, we can count the number of ties. And then the simple trick is to rewire each tie randomly with some probability P. Okay, in this case, it's beta. I think it's called beta. So beta is the probability that I take one of these ties from the picture on the left and then throw it somewhere in this matrix of adjacencies at random. Okay. And obviously, as I increase beta, you're going to get something that looks like this. When beta is 0, you start with this. Now, little simple point here. There's no reason why you have to start with a caveman structure. If you wanted, you could start with a hierarchical structure and then also use beta to randomize it, right? So think about a strict hierarchical flow of information in an organization where it goes from the top, right, with the tree-like structure like this. And then with some probability beta, you could rewire one of these so that you get a lateral tie or you get a tie that even goes backwards and so on. So you can kind of think about the general strategy here is to begin with a network of known configuration and randomly change it with some probability at the level of change of each tie. Okay. The advantage of doing it like this is as you smoothly vary beta, the probability, you're going to go smoothly from whatever structure you started with to a complete random graph at the other end. Right? That's the advantage. And the other advantage, obviously, is you're keeping the total number of ties constant. So any effect you get will not be driven by density. It's going to be driven just by topography. Okay, so it's a neat trick. And I think this is Duncan Watt's idea. And I think it's now become like a standard in the field. But it's a very neat modeling trick to kind of preserve density, change only topography, and smoothly vary between a known structure that you like. In this case, it's caveman. But that doesn't have to be the only one, right? We could have started with a completely different kind of structure. And then by tuning beta, we move it towards a random graph. Do you understand how this works? So you could start, if you like, with like a multi-divisional firm and then see what happens, right? Or you can start with like a flat team and then see what happens. So it's a fairly generic strategy, I think, of working with the interaction structure. All right, this is influence. Okay, what's the interdependence structure between actors? How does the payoff to my solution depend on what solution you are implementing?
think they try to do something like an NK model, right? They call it MS or something, but it's similar in intuition where you take an action, but it has a level of dependence on others based on the S parameter.
So does it have a dependence on the actions of others or the other actions you take?
I think it was others, but I am not sure. Okay. Sorry.
It's yourself.
Okay.
Right. So the idea here is there's like a vector of let's say zeros and ones. So let's say m is 5, then let's say it's 1 0 0 1. The value really here is in so the extreme case would be unless you get the exact configuration right, your payoff is 0. So it's like breaking a combination lock on a suitcase, versus it's a smooth gradient where for every bit you get correctly, you get some reward. That's what they're varying, right? But these are dependencies with an actor. There is no dependencies between actors. Okay, so it's a crucial point to appreciate. This is a model of organizational learning in which there is a network, but the network is capturing a structure of interaction which is only about influence. It is not about dependence. There is no dependence across actors. Okay. All right. So how does learning work in this model? What is learning and how does it operate at the level of the agent? You can actually pull up the exact definition here. So take a look and tell me what's going on learning wise and how does it relate to the kind of learning we've been modeling. So what's a belief set? A belief set is basically like, a set of something like this. Right? This is a belief set with m equal to 5. And if s is equal to 5, it means you got to get all 5 of them correct in order to get any payoff. So how is learning working here? And is this learning by doing? Is this vicarious learning? Is it coupled learning? What's going on?
I think it's an element of vicarious learning only, but what they're doing is there's a very specific rule where they use like the majority decision rule. So if most people undertake a particular configuration, then that's what the others learn is.
Okay, so there are 3 layers of concepts here that I want to unpack to make sure we understand. First, it is vicarious learning because as Piyush said, we're looking at what others have done, right? Look, and then based on that, we are trying to copy their actions. But it's more than that. It has 2 more layers. It's also got baked into it something called success-based copy. So it is vicarious learning conditional on the success of the others relative to you. So I'm not just blindly copying everybody, right? So there's a term for this. It's called success-based copy. Let's write it here. And it's a pretty good assumption in many circumstances because it's a lot like benchmarking. Right. So if you are a McKinsey or a consulting company and you're trying to sell benchmarking to a client, you're not going to ask them to copy some company they've never heard of. You're going to tell them a story about Google, right? So that's the same thing. So this is really the idea that you should copy, but copy only the successful, because your theory is that what you're copying is causally responsible for their success. Okay. So that's the second layer in this model of learning that's important to bear in mind. It is vicarious learning. It's not coupled learning because there's no dependence. It is vicarious learning. But it's vicarious learning based on success-based copy. The third element, because you have multiple neighbors in a network, it's not a dyad, right? How do I reduce the multiple neighbors in my network to something that I can learn from? Okay, and what I'm really doing here is a kind of averaging of everybody else into one super neighbor. Okay, so there are different names for it. I think there's something very similar people use in physics called mean field approximation. But the intuition is very similar. So when I look at a particular particle or entity I have many, many neighbors, but I can turn all of them into a super neighbor by averaging them in some way or aggregating them in some way. Here I'm aggregating them using the rule of majority. You see how that works? Let me make sure this point is clear because a lot depends on it. So let's say that, if it's just A and B, if there were just two people, then life was easy, right? When we're trying to figure out the impact on A of B, we just have to look at the effect of influence or interdependence of B on A. But suppose it turns out that there's B1, B2, B3, and B4, and A is connected to all of them, right? So what I'm doing is, and in this particular model, this B1, B2, B3, and B4 are the four people who are doing better than A. That's why it's success-based copying, right? But now that I've identified the four people who do better than me, I have to do one more step. And the one more step is I convert all of them into a single giant B, who's like the average of all of these people. In this case, it's not average, it's the it is the majority, right? So I'm going to go with the action that is being taken by the majority. So these three steps are buried in that one sentence. Okay, so there is vicarious learning. I'm copying what others are doing. I'm not copying everybody. I'm copying only the successful. And because there are multiple successful people, I'm aggregating them into a super neighbor. And the aggregation rule I'm using is majority. Okay, we will have to do something like this in any network model, because typically in a network model, you have more than one neighbor. So when we have to think about how the aggregate impact of the neighbors plays on you, you will have to use a rule like this. Some kind of averaging or majority or some aggregation rule that combines what your neighbors are doing into something that acts like a single super neighbor. Okay. All right. And then let's say they've got the majority of what their more successful neighbors are doing. Then at the last step, they're actually going to update their own dimensions to get in line with that of the majority with some probability p learning. So what does this probability p learning most resemble in our standard one agent reinforcement learning model? Which parameter is it kind of similar to? You should now have in the back of your head always the basic
phi, as in phi or phi.
Yeah, phi.
As in
Exactly.
Yeah.
It's your updating rate, right? It's the phi parameter, which is the one that you use to essentially model the delta between your old belief and the new belief through prediction error. That's what this is, the learning rate. Okay. So this is the susceptibility of you to change your belief conditional on seeing what belief it is you want to copy. So with what probability are you going to copy? So it works roughly like phi does. Okay. And here are the results. So I'd like maybe somebody other than Neti, to try and interpret the results. She gave us the setup of the model. So would somebody help us interpret the results now? What do we find?
I think what they're trying to say is somewhere like the intermediate values of beta is where they have the appropriate amount of exploration,
right,
or learning happening. Yeah.
Okay, so somewhere here at beta somewhere between 0.1. So it's like a very close to a corner solution, but it's not. Right. So this is really the interesting point, that if you look over the entire range, you might ignore this little bump and say it's generally declining with beta. But that's not accurate, because around 0, beta's behavior is very nonlinear, right? It jumps kind of dramatically. So really the story ends here. The rest is all just for the reviewers, right? I can't seem to write anymore, but it ends at 0.2. The rest is just to keep reviewers happy. The action is all over between 0 and 0.2, right? That's what's happening. Okay. So explain why this is happening now. Now that you understand how the model works, how the copying works, what's exactly driving this sort of result? Oh, before we do that, just I want you to pay attention to what is being measured as performance here. Okay, the performance here is the measure of success in that landscape in the final period, in the steady state. Okay, so remember we talked last time about search versus learning, and we said search task is one where you care about the max, but actually it could also be that you care about final. So this is an example where it is a search task where you really care about the final period performance. We're not really taking into account the cumulative over time. right? That's not really being measured in this model. What's simply being measured is the final period performance. So it's literally, whatever happens before equilibrium, we don't care. In steady state, what does the performance look like? For certain problems, that is not a bad way to go. In general, I think that only works if you are in a selection environment which is quite generous. So think about that, right? Suppose your performance looks like this. This is time, and this is your performance, okay? And your performance looks like this, even if it's completely monotonic, okay? And we say we're only going to look at performance in steady state or at some time period t. If you do it at a fixed time period t and only count this performance, then you're going to undercount the difference between a firm that looks like this and a firm that looks like this very dramatically, right? It might be that if your selection environment is very tough, by the time you're here, this one basically dies. So when selection is myopic, it happens in short time scales. It's usually a good idea to look at the cumulative effect of performance. So they're not doing that. They're just looking at the steady state performance at the end of the interval of time, right? That's what they're looking at, but that's what they have. Okay, so back to this point. So why do we get this result? What's the mechanism and how does it work? And you can use as a hint the picture on the right.
When there's like strong clusters in the within the organization, then the information within the cluster becomes redundant and homogeneous. Whereas you have a kind of semi-isolated, which is called here, but like a link, kind of weak link between the subgroups, that you can preserve the variety of information between the groups. So I guess
how does it translate into performance though? So why is it that this kind of structure where there is some clustering, but at the same time there are some ties across clusters? Why is that good for performance? So you don't want beta to be 0, right? With beta 0, you have this structure, the one on the left. So in the one on the left, there are connections across the caves. It's not like completely blank, right? So why do you want at least some degree of beta?
Is it, if we take the benchmarking example, then beta equal to 0 will be basically you are copying no one and trying to make sense of it by yourself. And then a small amount of beta is still that you are with the small probability trying to copy from other people without emphasizing too much on like this one person you copy from. So you get a larger diversity of beliefs or like more, there is more information for you to like revise your beliefs from. So it's almost like you now have 10. So let's say beta is 0.1. So you're copying from 10 organizations, each with a probability of connecting is like 0.1. So there's more diversity of information.
And what happens if you copy from lots and lots of people? If the beta really gets tuned even higher, what's the problem then? If you're connected to, not necessarily copying, what happens if you're connected to many, many people?
You might also get like contradictory information, and then you're no longer sure what works.
Okay.
It's fair to know like what's the really best for you. So before you come to the kind of optimal decision making, you are interrupted by others' informations.
So others can disturb you off your path to improvement, right? If you're listening to too many of them, they might actually push you off the path to improvement. Okay. Any other way to think about it? Did you see the connection? Yeah. So go ahead.
No, I think similar to the tau parameter in single agent model. So as the tau increases, there is like a inverted U curve. So more exploration at the very high end and very less exploration at the low end.
Okay. Except what does this exploration mean in this model? Does it mean the same thing as in the single agent reinforcement learning model?
No, so as in you're looking for a configuration here, like it's similar to an
It's more like NK, right? This is actually closer to an NK model than it is to a bandit model. So again, we discussed this in session 1, I think, or session 2. The terms exploration, exploitation are kind of used both for taking an action that's not your first best in bandit, as well as searching away from your local configuration in a rugged landscape world. They're using it in the second sense. Okay, but of course these things are intimately connected, because obviously the further you go out in general, the less you know about it. So that might be connected to the idea of risk taking. So we've had this discussion before, but just to remind you, exploration can be used in this polysemous way to mean either the taking of actions that are not your current first best, or it could be used to refer to the idea of taking long jumps in the landscape, right? And there is a rugged landscape at work here, which is the vector of zeros and ones. So this is a model of organization learning, right? It's a multi-actor model. It has vicarious learning inside it, but it does not have coupled learning. And it is looking at ties, which are influence ties, which are all symmetric. Okay, so these are ties in which flow of information goes in either direction. So the influence is symmetric in these structures. So this is a particular model of organization learning. Make sense? Okay, let's compare it to another one, which is the Friedkin and Bulow paper on opinion dynamics. So who would like to go take a shot at explaining this one? What's going on in this model? One and three are really the, I mean, 3 is derived from 2. 1 and 3 are really the key equations in this entire line of work, not just this paper. You've seen this before, shouldn't be new.
So, as in so what I understand from one and how it's different from the previous paper is that previous paper we were trying to, as you described, like there's a 2-step process of learning where we are first looking at success and then calculating a majority. Here we're not doing anything like that. We are looking at all the members that you are connected to, and you're basically doing a degrouped averaging of belief as in you're doing a degrouped averages of as in the beliefs across.
Of the beliefs, right? So it's taking all of their beliefs and putting the weights W on them. So W in this is basically the weights on these people and taking the average of them. Plus there is this element here, which is introduced by, this is not in degrouped averaging, but it is the, I don't know why my pen occasionally stops writing. Okay, here it is. So what's that term doing? This is not in degrouped averaging, but it is there in the Friedkin and Johnson models. What is this doing?
Is it like an initial imprinting effect of?
Yeah, so it's like an initial, so it's like some measure of, AII is some measure of your stubbornness to social influence, right? So what you started with, you always retain with some weight. The rest of it, you're willing to update with weight AII, and that is being then using the degrouped averaging to create your super neighbor. And that super neighbor is then the one that is affecting your beliefs, right? That's what this is doing. So this is essentially like a sophistication on degrouped averaging. But as they point out here, in the special case where A is equal to identity matrix, where essentially you don't have a initial bias, then the model reduces to a degrouped system in which the equilibrium is this. Okay, in steady state, it's going to be exactly equal to that. Okay, what do they show with this model? There were 2 papers that you ended up probably looking at because I had given you the wrong one. But either of them, I think the spirit of the results is actually remarkably consistent. What do we take away from these papers? If it helps, think about it as a contrast, right? Think about how this is different from the paper we just saw. Both are networks, okay? Groups of actors connected to each other, both have neighbors, both have done this super neighbor process of constructing a referent agent. to capture the effect of influence. So what's different? What are they doing differently?
So is it the case that in the Fang et al. Paper, you search and then you decide how you want to revise your beliefs? Whereas in this, it's more you are updating your beliefs from interpersonal influence.
Yeah, you're absolutely
I
on the
think
right
it's
track.
the sequence of how you are learning is different.
So what's the learning in this story? What is being learned? When we say organization learning is change in belief or behavior due to experience, what's the learning here?
So in this model, it's revising. So the weightage you assign to the beliefs, right? So revising your belief system, and
it's your beliefs are changing. And then of course, in both papers, they also talk about how the W's themselves can change, right? Through a process of self-reflection over time. So if you find that a particular individual is very close in their belief to what the final belief was after discussion, that individual's influence becomes larger. This is called reflected influence, right? It's mentioned briefly in both papers. So here's the intuition. Let's say we start out in a group discussion on a topic, okay? We don't really have like a structured topic. We all come into a room and we start talking about something. And we first begin by each stating our private opinion. So the plan is, what do we do with a free day this weekend? How do we spend it? Okay, so I say, let's go to Bulow. Win, you say, let's go gambling in somewhere. And somebody else says, let's write bandit models. Okay, so there's like a bunch of different views on how to spend Saturday. Then there's a lot of discussion. We talk to each other, we listen to each other. In the end, we make a decision. Okay, let's say the decision looks like, let's write bandit models. What this model suggests is that the person who had that idea in the beginning, their influence should get updated, because effectively what people are seeing is that this person was quite influential in this discussion, right? And if you, so whoever ends up being close to where the final discussion was, I think there are variants where they look at the final view of people and the group versus initial view of people and the group. In this paper, actually, I think it's the final view. I'm sorry, I confused you. So in this one, it's actually the final one. So we start out by writing privately, where do we want to go this Saturday? Okay, we have a discussion. We look in the end, and then we again ask privately to write down what we wanted. And if it turns out that what you wrote in the end privately is the group decision, then you effectively become more influential on the group going forward. So your W gets updated. So there are two kinds of learning happening here. There is learning from each other, vicarious learning, okay, offline, because there is no feedback from a task environment here. So this is a complete offline learning process, unlike the Fang et al., where they are getting feedback from the task environment based on the actions they're taking. Here, there's none of that. It's a completely offline vicarious learning process. But the organization is also learning about how to create weights on different individuals. So when each individual is creating their super neighbor, whose voice gets heard loudest in creating that super neighbor? That's the other kind of organization learning going on here. Okay. So it's really, if you like, a kind of way of thinking about how influence or expertise is recognized in a group, how some people become more influential or more powerful in a group, even if you all start out equal. These are the kind of models that can help us understand, particularly the versions where the W's change, right? So that was explicitly in one of the two papers. I can't remember which one, maybe the science reports one. Yeah, I think it was in the science reports one. So these are ways of thinking about organizational learning, which are purely offline. There's no feedback coming from reality, which means it's not as if some of these opinions are objectively right and some are wrong, right? Because we don't get any signal from the task environment. They're just showing that given an initial distribution of opinions and given this network of influence structures and an updating process, it will converge given enough time to a steady state, and they can predict it pretty well with the data and that they are able to gather, right? So their models are doing a very good job of predicting what actually happens. And their basic point is you need the at least one of the individuals in the group to have that opinion that eventually becomes the one that the group converges on. If they're not there in round one, it's not going to appear miraculously. So it has to be there. But if they're there and the network structure is one that allows support for that truth, then it will emerge as the winner, right? That's what they call truth supported. So you need the truth and you need the support, and then you will actually get the outcome. So this is a different model of organizational learning, which is also based on networks. And the key difference really is this is an offline model. Okay, there is no feedback coming from the task environment. It's also different because in some sense, the network itself is endogenous. How is the network endogenous? Even though the pattern may be the same, the weights are changing. Okay, so that makes it a very sophisticated model. It's very different from the other one where the network structure itself does not change during the interaction. But here, if W's can change, it's actually a very powerful way of changing the network while the model is running, right? I think that's really like the most sophisticated way of thinking about this. And they have a very rigorous formalism for at least the equilibrium outcomes. I don't think you can get much insight about the process. You have to simulate it. But if you want to understand what happens if the process runs long enough and an equilibrium is reached, they have beautiful results showing us what will happen. Okay, so you can literally plug and play these things. So this class of models where it is offline and it is purely about opinions diffusing through a network over time are called opinion dynamics models. Okay, it's also a kind of organizational learning, but with this caveat that it's completely offline. All right, so these are like two very different ways, if you like, of thinking about org learning using networks. Both are using the technology of networks, but they're using in the end fairly different logics of what's underlying the process. So can you think of situations where this model is a better representation of what's going on versus the previous one, and vice versa? So for what kind of problems would you use opinion dynamics models, and for what kind of process would you use the search on networks model of Fang et al.?
Is opinion dynamics more relevant where close interaction between group members in a decision-making process is required? There has to be interpersonal exchange of, like on whatever you're deciding on. Whereas in Fang et al.'s paper, it's like we described, like for benchmarking, you don't always need to actually talk to the other person or even like just observing them without in very deep interactions works fine.
Yeah, so implicitly the Friedkin and Bulow and Friedkin and Johnson models that come before this are operating on something that looks like beliefs in our structure, right? Whereas the Fang et al. Is operating on something that looks like actions. So you're quite right. You could apply the Fang et al. Model in situations where all you need to observe are the actions and the outcomes. Whereas you could use the Friedkin approach where you want to actually spread beliefs in the network. Okay. Now, remember, they're just doing it for a single, it's a scalar, right? Yeah, these are scalars. So it's xi0 is drawn from real. So it's a scalar. So they're not really looking at it as a set of beliefs about a set of arms in a bandit. It's just a single number. It's an opinion, right? But one can generalize this to a vector of real numbers, which are the expected payoffs for the different arms of a bandit. Okay, but still all beliefs. That's the idea. Whereas in the Fang et al. Model, you're really looking at copying actions. So this is an important difference. What else? What else would be different between these two circumstances?
Maybe the difference between feedback and no feedback. So one is where about organizational performance where you get profit reports or analysis. The other could be something like diffusion of fashion or ideas from one place to the other, where there's no one right or there's no one value to which you're getting feedback on. It's just how one thing propagates across it.
You could also do that within a strategy making discussion, right? That's an offline process. So if you're looking over a long enough period of time, then you make the investment, you get some result, then there is the usual learning by doing. But this could be a complete offline vicarious learning process where we're in a boardroom, we're all discussing our life experiences and we are weighting each other's opinions using W's, right? And reaching some convergence based on that conversation. So you can use this as a way of an offline discussion process, whereas the Fang et al. Model might be more like an online learning process, except that there's only vicarious learning there. There is no coupled learning, okay, in Fang et al. Okay, let's move to the third one. So this is our paper with Kochak and Leventhal. So here we are looking at structures of influence networks, and we are comparing these three kind of structures. There's the crowd, right? There's a flat team where everybody is connected to everybody symmetrically. And there's a hierarchical team where everybody is connected to everybody, but one of the actors is connected asymmetrically with the others. Okay, so it's just a very simple two-layer hierarchy. So that's why it's a hierarchical team. I think calling it hierarchy would be stretching it, but you could easily extend this, as we do in the paper, to multi-level hierarchical structures. But the basic point here is that there are these different structures of influence. Now, where I think we made a couple of interesting innovations is we can use the same network approach to also map dependencies between people. Okay, I mentioned that earlier. We can use networks to map either influence or to map dependence. Right? Here in this picture, it's being used to map influence, but we could also use it to map dependence. And we do it in extensions. In the baseline, we assume a particular dependent structure between all actors. What's that structure? What's the baseline dependent structure in this model? Wasn't clear? Okay, let's break it down into two parts. You remember this? This is how we looked at a pure search problem where a single actor is searching among actions, right? That's the standard bandit model. We said, suppose there are two actors and we want to model coupled learning, then we have to think of it like a game where the payoff to each actor's action depends also on what the other actor is doing, okay? And obviously games, depending on the payoff structure, can have both search and coordination. So I need to find the best action and I also need to coordinate on it, right? Both things are going on. How do we go from 2 actors to n actors? This is really the crucial modeling innovation in this paper. So we have this, we know how to think about different kinds of dependence for 2 actors, but how do we go to n actors? So this was the approach. Okay, you have S alternatives, each of which has some intrinsic payoff. And one of these we are going to set to a global peak. So it has a value of 1. The remaining alternatives are going to be drawn from a uniform distribution, which goes from delta 0 to delta 1. Okay. And one way to think about it is the cost of imperfect search, which means landing up in the wrong action, increases as delta goes to 0. So the opportunity cost goes up if the deltas are small. So this is all pretty straightforward. Now here comes the crucial thing. Let's define a measure of convergent behavior in the system, which is the fraction of agents making the same choice as you in any period, right? And let's parameterize the effect of that convergence using chi. So chi goes from 0 to 1. And now I'm going to write my payoff equation like this. Let me rewrite it here, because we want to really understand each part of this to figure out exactly what's going on. Okay, so what's going on here? So how do I interpret this equation first? Remember, Vik is the raw value, right? Which you seeded in the arms. That was pretty straightforward. Let's say you had multiple arms. One was always picked as having a value of 1, and the rest go from delta 0 to delta 1 uniform distribution, right? So you could end up with this, something like that. So delta 0 and delta 1 tell you the rest of the arms, and the peak is always at 1. Okay. How do I interpret this thing? F is the fraction of other people who are taking the same action as me, right? So let's do it mechanically. Let's set chi equal to 0. So if chi is 0, what do I get? I just get the raw payoff, right? That's just a standard single agent reinforcement learning bandit problem. If chi is 1, what do I get? This disappears. And my payoff for the action gets scaled by the fraction of others who've taken the same action. Right? So rewriting it like this, maybe make it more or less intuitive for you. I'll leave it to you, but they're really saying the same thing. It's just rearranged. The point really is that when chi is 0, it's as if you are playing alone. When chi is 1, it's not enough if that you pick the right action. It's important that others pick the right action too. Okay? That's the crucial point. So it's a way of factoring in not just search, but also coordination, because you want people to also land on the same global peak as you. Now that immediately you can see create some interesting effects, because if chi is high, okay, it's quite possible that all of us converge to the wrong action. Why? Because it's being rewarded for doing that, right? You're getting a high premium. So there's no penalty because you're not paying the penalty for non-convergence because you're converging. So even if you know that there is a better action around the corner, okay, you're not going to take it. Why? Because you take that action, nobody else takes it. Your F is going to be very small. And if chi is 1, your overall payoff is going to be very, very small. So this is really setting up a trade-off between search and coordination. So when chi is 1, both matter. When chi is 0, only search matters. Okay. And when both search and coordination matters, it means that now we have a landscape in which there is a risk that people might get pulled into the wrong action because they are collecting there. There is some gains from being at the same place. So a good analogy would be something like, we want to go to a party on Saturday. Okay. And ideally I want to go to a place which is happening. Something is happening. Lots of people are there. But I also want to go to the place with the best alcohol and maybe with the best prices on alcohol. Alcohol is generic. Okay. So the place is the best deal. So now I have this combination of problems of search and coordination. Right? That's an example. Another example might be something where we are working on parts of a complex technological system where we want to take design decisions which are compatible, but we also want to find the design that's a global peak. Right? We don't want to settle for something that is low class just because everybody is kind of converged on that. So this is the dual problem of search and coordination that this task environment is able to produce in one shot. Okay, and we can do this for any number of actors, because remember the trick with multiple actors is you always have to find a way of converting your neighbors into a super neighbor. Where's the super neighbor here? It's hiding here. Right? This is where the super neighbor is hiding, because it's a measure of convergence, right? It's telling you how many others have taken this action. Now, how do I take this structure, okay, and marry it to the idea that the dependence among actors might vary also by a network structure? Because if you look at this equation, this is implicitly assuming that you're dependent on everybody else. Because F is 1, if everybody takes the same action, that's when you get the full payoff. If even one person takes the different action, you get a little less payoff. This is really the same as assuming a network structure where everybody is connected to everybody else in the interdependence structure, right? How can I make this a bit more sparse? So using the same equation and using the network structure, how can I change the model in such a way that I'm going to say, it's not everybody, but only the people I'm connected to in the dependence network. They're the ones whose convergence should matter. How would I do that?
As in using exactly the same equation as the Friedkin's model. That it'll look exactly like what it had. So I think they had AI and WIJ. So WIJ would be how much you are putting weight on the others, and then the AI would be how much you are putting the weight on your own, as in.
So good intuition, but that was about influence. Remember, we're talking about dependence.
Yeah, but the equation would look exactly like that, as in, even though it means something different, but shouldn't it look, it should look the same way as the Friedkin's equation.
Yes. So what you really need is some way of converting this fraction,
Yeah.
how many converged, into a number that goes from 0 to 100 as long as the people you're connected to are taking the same action. So it doesn't have to be everybody in the system, right? The denominator is not n, but the subset of your local neighborhood you are connected to.
Yeah. So it would not be like an FKT, but it would be like a FIJT, where FIJ is the people, as in the
fraction.
Yeah,
exactly. Okay, now I see where you're going. Yes, that's exactly what it is. So just by changing f, right, which currently is defined as the fraction of the total number of agents, instead of that, we change it to the percentage of your connected agents. Everything else can remain exactly the same. Okay, so we can then embed different dependency structures and then use that to compute whether or not you are in convergence with them or not. So that's as far as the dependency side is concerned. Okay, we're still thinking about actors who are effectively asocial, in the sense they're not really exchanging any beliefs or even observing each other. They just happen to be in a task environment where they take actions, and the payoffs partly depend on what other people are doing. Which other people? In the baseline model, everybody. You can easily extend this to a particular network of people you're connected to, and whether they are taking the compatible action or not is going to determine your payoff here, right? Okay, Shruti?
So Phanish, is another way of understanding this model, it's like similar to the MK model, apart from the fact that K there is probably interdependence between tasks, and here you are saying K is interdependence between actors, in a way that it contributes to the final. And so basically it's the same NK landscape problem, but translated when each of those K actually represents other actors who need to take action so that you can reach the optimum.
Yeah, absolutely. You can think of it like that. This model's sole purpose is to make it easy to create dependency between actors and between large numbers of them, right? The NK approach is very good for modeling dependency between each bit. So unless each actor is flipping a separate bit, it becomes quite difficult to model interdependency between actors. Here, Chi is playing the role of modeling interdependency between the actors via this convergence fraction. So we can model interdependency between large numbers of actors, right? Which can be arranged in any network configuration you like, as long as we use that to compute the F. So it is really a model for modeling interdependence between actors as opposed to between actions. That's exactly what it is. Okay. Okay, so this is as far as the dependence side is concerned. What about the influence side? How are we going to take into account the beliefs of actors about these actions and how they spread through the network with each other? Right. So far, we've been talking about the dependence network, but we said we wanted to model these different networks, not just of dependence, but also of influence. Okay. Hopefully you're following, right? The point is the same network structure can be used to model either. So if it's like a crowd structure where there's no dependence at all, that is the same as saying Chi is 0. Okay. If it's a fully connected structure like the flat team with the dependence structure being saturated, that's this equation. Okay, where Chi is non-zero. How do we now flip this and use the same network structure to understand the effect of beliefs of one actor on the beliefs of the other? You've already seen that. That's Friedkin, right? That's degrowth averaging. So effectively, I can take my vector of beliefs about which actions to take and your vector of beliefs to which actions to take and combine them through some kind of weighted averaging process. Okay, so we use exactly the same weighted averaging process as degrowth, not Friedkin and Johnson, because Friedkin has this initial bias. So we don't have that, but we have the degrowth version, which is a simplification. Actually, you could argue the model we have does have the initial bias. because the way it works is over a period of time, actors first learn from the task environment through reinforcement learning, and then they share their beliefs through vicarious learning. And then they go through iterative cycles. And as you know, in reinforcement learning, your initial beliefs continue to have a weight forever because it's iterative, right? So there is an implicit weight on your initial beliefs even in our model. So I think it is, you could argue it is fully consistent with a Friedkin-Johnson type approach. But these are the two components that are really being pulled together. So just to make sure that we understand the task environment really well, I've broken down the key parameters in the model into these 4 boxes. Okay, chi is 0, chi is 1, delta 0 is 0, delta 1 is 1, delta 0 is 1, delta 1 is 1, and so on. So I'd like you to describe for me what's the kind of task environment in each case. What situation does it correspond to? So let's take the situation here first. The first one on the top. So delta 0 is 0, delta 1 is 1, and chi is 0. So what's happening in this task environment? You can draw it out for you if you want. So delta 0 is 0, delta 1 is 1, which means essentially you have one global peak, which is always going to be at 1. And then the rest are kind of between 0 and delta 1 equal to 1. So that's the range of the rest. Okay. And we said chi is 0. So what kind of a task environment is this?
Your
What's
optimization?
Yeah, it's a pure search problem. You could say it's a pure search problem, right? I just need to find the best action. Okay. And if I want to care about payoffs over time, then it's a bandit problem. So I would take into account the cumulative payoff over time. But this is just a question of finding the best action in the landscape because chi is 0. What if delta 0 was 1, which means all the payoffs look the same? They're all 1. What kind of a problem is that?
Purely coordination problem.
No, because chi is 0.
Okay. Okay.
So this is neither search nor
Yeah, this is-
coordination, right? This is a non-problem. It says everything works, life is wonderful. You don't really need to search for anything. Okay. What about the case where you have delta 0 to 1 like you did before? You had some low payoffs, you had some medium payoffs, you had some smaller ones, and then you had a 1. Okay, so delta 1 is 1, delta 0 is 0, and now you have chi equal to 1. Right? So every actor is looking at a set like this, but remember, whenever I land here, I don't get this raw payoff. I get this payoff scaled down by the fraction of other people who are also picking the same thing through the F, right? So what kind of a world is this?
Both search and coordination.
Okay, both search and coordination matter. And then finally, what if all of these are 1? If all of these are 1, okay, and chi is equal to 1. What is that?
It's purely coordination.
It's pure coordination, right? It's like a matching game. So we really need to just agree on one. It doesn't matter which one we agree on. It's like an arbitrary standard, but it does matter that we all converge on one. Okay. So these are some basic task environments that we played with, as you remember from the model. And here's what the key results look like. Okay. So we struggled a lot, by the way, to find a way to visualize this. I remember we did multiple ways, but then Ekin actually solved this for us by finding a way of using color coding to represent the differences. So this was really the thing that the reviewers really liked in round 2. Otherwise, they were like very unhappy with the way we had done it earlier, the way I had done it earlier. So what this shows is actually the comparison of the 3 forms, right? So the green is the flat team, the hierarchical structure is the red team, and the crowd with no connections between them of influence. We are talking about influence structures here. That's the blue one. In all cases, the dependent structure is a fully saturated structure. Okay, so remember, we can talk about 2 sets of networks on the same set of agents, right? So the network of dependence in all these pictures is identical. It's a fully connected network where everybody is connected to everybody. And that makes sense in small teams. I think in larger groups, it doesn't make sense, but small teams, fine. What we are varying here is the influence structure. So we're comparing the flat team to the hierarchical team to the crowd. And what's varying on the x-axis here is the is delta 1, and on the y-axis is delta 0. Okay, you should be able to see why that's the way to do it, because delta 0 is always less than delta 1, which is always less than 1. Right, so that's why you're seeing there's nothing in the top part of these pictures. Right, so when delta 0 is 0, delta 1 can go all the way up to 1. But if delta 0 is 1, then delta 1 can only take on a value of 1. That's why the top left hand of these pictures are always empty. Make sense? Okay, so this is really packing a lot of information into one graphic. So that's why I'm explaining it step by step. So the x-axis is delta 1, y-axis is delta 0. The depth of the color is telling you the performance advantage over the next best structure. Okay, so it's telling you which of the structures wins in which space. The columns are telling you 3 values of chi. So chi is 0 is the pure search world, parallel search world. Chi is 1 is the coupled learning world, where there's dependence between actors that's forcing the dependence to be taken into account. And the rows are time periods. So it's telling you what happens at the end of 50 periods, at the end of 100 periods, at the end of 500 periods. Okay. All right. So firstly, how do you interpret this? In plain English, tell me what's going on. Hint, if you need some help, you can look at the appropriate place in the paper.
Let me try one. So I think what I remember from the initial parts of the paper is about is if the time period is small and now looking at this graph when you require coordination. So if I'm looking at chi is equal to 1 and I'm looking at the top right parts in t is equal to 50, that is where the hierarchical teams would do better.
Exactly. So under short time period and high dependencies, hierarchy does well. So there are two interesting puzzles to explain. Why is it that one of them is actually easier to explain than the other? Why is it that given no dependence and doesn't matter what the time constraint is, that the flat team does better? In the first column, you can see everywhere, right? No dependency, the flat team is winning everywhere. And surprisingly, why is it that despite dependencies, given enough time, the crowd actually does better? Right? Both are really interesting things to be, a full theory should be able to explain all. It is intuitive that, given time pressure and dependency, hierarchy should do well. Less intuitive is why is it that given more time, even given dependencies, the crowd can actually end up doing better? And why is it that under parallel structures, you actually need the flat team and the crowd is not enough? So what's going on? So to help you think about this, remember we have equalized everything in this story. The dependency structure and the payoff environments are the same, right? The only thing that varies is the pattern of influences through the networks. So if it's a crowd, it's just a collection of individual actors learning on their own. If it's a flat team, everybody's exchanging beliefs with everybody else. If it's a hierarchical team, everybody's exchanging beliefs with everybody else except the boss, who doesn't change his mind based on what anybody else is saying, but can influence everybody else to some degree, right? Not completely, but to some degree. So how do we understand what's going on, given that this is how the belief dynamics look in the three structures? Let's start with these. Yeah, go ahead.
Can we say that, like in the case chi equal to 1, they are independence? In the short period of time with hierarchical team, it's easier for them to coordinate with each other. But then in a longer time period, the crowd is able to figure out individually what are the best alternatives. So they can outperform the hierarchy because the hierarchy is less explorative compared with the crowd.
Yes, so that's exactly the right intuition. So given that there are dependencies in the last column, right? So the agents have to figure out how to coordinate for themselves. But in this model, the key point really is that there are two forces of convergence in the model. one is bottom up. Even if people don't talk to each other, because they are dependent on each other, and the feedback comes from this equation where the chi and the f was written earlier, right? So even without talking to each other, if our feedback is telling us if our actions are compatible or not, given enough time, we will find the right compatible actions. That's bottom-up convergence, right? Okay. The alternative is for somebody at the top to make everybody converge because they're spreading their same beliefs to everybody. So convergence can happen bottom up by agents learning autonomously without talking to each other, but from the same task environment. Or convergence can happen top down where one individual is giving them their worldview and explaining it to everybody. Both can produce convergence. Okay. In fact, the top down produces it faster. The problem though is that it might converge you to the wrong thing. You see that? And you can see even in the picture on the top, where is the advantage of the hierarchy strongest? It's not in all, the entire space is not uniform. It's actually in the case where delta 1 is quite high. So what does that mean? If you go back to our picture here, what does it mean that the advantage of hierarchy is highest when delta 1 is quite high? It doesn't matter what value of delta 0 is. For all values of delta 0, as long as delta 1 is high, then the hierarchy does pretty well. What is that telling you? Yeah, Shruti?
Sorry, I had a question, not an answer to your question.
Okay, go ahead with your question first.
What is the mechanism behind convergence in a crowd? So this is a pure coordination problem, right? Where chi equal to 1 and every action will have like an optimum outcome. So, but are they talking to each other? Because in a crowd, there's no interaction, right? So what's leading to convergence?
Think about it. What is each actor reacting to? The feedback they get, right? But the feedback they get is conditioned on what other people are doing. So let's say, okay, let me give you an example you're already familiar with, and then you'll see the intuition. You remember the game where we played matching between two actors, where the payoffs are like this? And if both of them were learning by doing between these two choices, we showed that they were able to reliably find either one of these. How did they do that? So as far as I'm concerned, I don't even know that you exist. I just have two actions, and when I take number 1, I sometimes get 1, I sometimes get 0.
Okay.
And the same is true for you. But if we land often enough here by chance, we're going to reinforce that very strongly and end up taking that action again and again.
Yeah, okay. That's why you need a longer time horizon to do.
Exactly. So given enough time horizon, this system will converge bottom up. That's what I meant by bottom up convergence, right? The top down convergence is much more straightforward. There's one guy telling everybody, guys, come to this action. Okay. And if everybody listens to that, they end up there and they get convergence. So what you're seeing in the top right-hand corner is the advantage of hierarchy for rapid top-down convergence, which is only really an advantage when delta 1 is high. In other words, your next best option is also pretty good. Okay. That's what delta 1 is, right? It's your next best option. But if delta 1 were to shrink and become small, what is the hierarchy then doing? It's pulling everybody into the wrong action very fast. Right? So that's what hierarchy does. So hierarchy really is surprisingly the right thing if you want an agile team with lots of dependencies in them. If you define agile as getting good answers in the short duration, hierarchy does it for you because it gets people quickly converged to good, if not perfect answers. Okay. If you want perfection, you have to wait for a long time. Then the crowd will get it, but it will take very, very long to eventually get it. And the reason it will do better than the hierarchy is, unlike the hierarchy, there isn't one actor kind of artificially converging people to the wrong answer. So there's enough time in the system for everybody to explore. So given enough time, the crowd will beat the hierarchy, even in a world with dependencies, right? Which is quite surprising once you think about it, but that's what is happening here. How about the flat team? So in the world where there are no dependencies, why is the flat team better than both the crowd and the hierarchy?
Because you still need to search for optimum solutions.
Okay, but the crowd can do that. What is the mutual influence accomplishing?
More accurate belief structure.
more similar belief structure.
Similar belief structure. Yeah.
But why is it still ending up performing better? Because all the influence structure does is it says we share our beliefs. Okay, so what? Think about degrowth averaging. Remember what I told you it does? If I take your beliefs and mine and averages them, it does two things. It makes our beliefs similar, but it also makes them fuzzy. Okay? Fuzzy beliefs are a way of creating exploration. Okay? So that's the advantage of the flat teams. The flat teams are a way of preventing premature lock-in for individuals. So individuals on their own, right, for a given level of exploration have some risk of being locked in. But if you put a bunch of individuals in a team where they influence each other, they prevent each other from being locked in too fast. So flat teams add exploration relative to individuals. Okay, that's a good thing if it's a pure search problem. If it's a coordination problem, then there can be too much exploration. You might be making each other dance off the peak. And if you have dependencies, then you fall off, then it becomes very hard to come back again, right? But in parallel search, that is less of a problem. So the extra exploration created by these flat teams is actually an advantage. That's the reason why the flat teams will beat both the crowd and the hierarchy in a world where there are no dependencies. And we can actually show this to be the case by doing a simple test. The advantage of the flat team should get even stronger if individual agents explore less, right? So if you were to reduce the tau for all the actors down to a level where they hardly explore, then the flat team's advantage should be really, really strong. Because the flat team is building in the exploration that the individuals can't bring into the system, right? So you can use that like a mechanism test, which is exactly what we do. So we show that as you tune up the advantage of the individual level exploration, this advantage of flat teams goes away. So it's quite interesting what flat structures are doing. They're creating a system which destabilizes people's beliefs by preventing them from becoming sharp too fast. That creates exploration. That then creates finding something right, which then of course spreads rapidly and similarly through the entire system. In contrast, what the hierarchy does is it creates uniformity, but not with fuzziness, because it's one guy's view being imposed on the rest. It's not being averaged with equal weight, right? Therefore, it keeps people's beliefs sharp and similar, but it might be about the wrong thing. Okay. The flat team keeps beliefs similar but fuzzy, which allows for exploration. So that gives you the three corners of this graph. That's what's happening. Given enough time, individuals just left on their own will figure it out. So there are a couple of interesting high-level insights from this. One is social structures are shortcuts. Okay. Really, we should think about social structures as shortcuts. So once you are in time pressure, then social structures start to matter. So look at T equal to 50 rho. Okay, there's no crowd anywhere there. It's either the flat team or the hierarchy. So when you're short on time, then social structures help. And when are you short on time? We just discussed this earlier, when selection pressures are strong. So if you're in a world where there's a risk of being killed every 10 periods, then social influence can be very powerful. Okay, but of course, what kind of social influence structure is a function of the dependency. If you're in a world of parallel search, then you want flat structures. If you're in a world of dependency, you want a hierarchy. Okay, but neither of them is perfectly solving the problem, right? Each of them is imposing their own additional penalties as well. So this is the reason why in that corner where the time duration is short and there is dependency, you can see a dominance of hierarchy. But once you allow for more time or you tune down the chi in the system, then you get either a crowd or you get a flat team. Okay, so this is really the core point of this paper. We have to write something to propagate the thing in the public media. So I decided I will write it as a haiku. Okay, tell me if this one resonates for you. It does follow the constraint of 575. So it's really trying to capture the idea that if you are in the crowd, you can get trapped because you're not exploring enough, right? If you are in the social world, you can explore too much because of the mutual influence process created through degrowth averaging. But hierarchical leaders are kind of finding a balance between the two, as long as, of course, time is short, right? If time windows are infinite, then this doesn't hold. But given time constraints, what leaders really are doing is avoiding both. Now, the best is, I'm saving for the last. The key point here really in this story is actually the fact that the guy at the top in this hierarchy is no smarter than any other actor in the system, right? So we've created a hierarchy where there's no knowledge advantage at the top. There is no control of the guy at the top over the actions of those at the bottom. There's no incentive conflict. So all the standard reasons people give for why hierarchy is useful are taken out of this model by construction. Okay, is that realistic? No, it's the opposite of realistic. But the point was precisely to show that even if you take away all the usual reasons for why hierarchy is supposed to be useful, we can show you one new reason. And the one new reason is hierarchical structures of influence balance this exploration-exploitation problem by avoiding the extreme fuzziness of beliefs that you get with flat structures, but at the same time getting enough similarity in beliefs through the hierarchy to enable rapid convergence when that's what matters, when time constraints are real, right? So that's really the point of the paper. This is what it tries to show. And along the way, of course, we have created a platform which I think can be potentially useful for other things as well. Okay.
Just want to point out the subtle technicality there as well. When there is no interdependence, when you look at chi equals 0, these results are at the population level, right? We ran 1,000 rounds, we averaged them out, and we looked at them. So in a way, it's very interesting. When you look at chi equals 0, crowd and the hierarchy at the population level is actually exactly the same, because leaders take whatever actions they want, they get the feedback, they act like a crowd member, and everyone has to follow, and they cannot give feedback. Whereas if chi was 1, they give feedback in a way through payoff structures, but at chi equals 0, actually at the population level, you'll find that crowds and hierarchies act exactly the same, but then chi equals 1 breaks that, and that's why all of this appears. But it's a technical multi-level difference there that is interesting to interpret.
Yeah, and I think it's embedded in the point we made earlier that in these systems, there are two forces of convergence, bottom up and top down, right? Bottom up is coming through chi, top down is coming through the hierarchical structure. And they can interfere with each other, right? That's really the point. So what these pictures are showing you are the configurations where the net of those is either good or bad, which is why hierarchy is not always winning. It's winning in some places, but not everywhere. So there are multiple ways one can interpret the result, but as long as that core insight that is buried in that haiku is clear, sociality, flat sociality, is about exploration, right? Hierarchy is about convergence and similarity. Individual exploration can lead you to being trapped because you might underexplore. So given that individuals underexplore, social influence structures can increase the exploration, but it may be too much if it is flat, and it might be too fast if it is hierarchy. That's really the point of these different influence structures and how they work. Yeah, Shukti?
I mean, in a way, you are saying that it doesn't really matter who gets promoted as a boss, as long as there is a structure. So all this meritocracy based or like, tournament, none of this matters because their beliefs are in, like your assumption is their beliefs are no different from the rest of them. So
Correct.
anybody can be a boss as long as they are average.
Absolutely. No, this is very true. Now, from that, I will not jump to the conclusion we should stop promoting smart people to the top, right? Remember the difference between mechanism and phenomenon. This is one mechanism. So it says one of the mechanisms through which hierarchy works is simply the shape of the structure, independent of who is occupying the roles. Independent, that's what we prove. And to prove that, we really set up a system where there is no difference between actors. There is no incentive problem. There is no control. None of the standard stuff is there. But that's not the same as saying the standard stuff doesn't matter. Right? So I would make that distinction, I think, carefully. Yeah. Again?
I'm sorry, I'm jumping in a lot because we thought a lot about these things as well. At the same time, I think it's important to consider the variance in performance outcomes. We have one counterfactual, one line of time in reality, right? And if we don't choose, of course, smart leaders, then it's interesting. The simulation shows that the hierarchies perform better, but with a higher variance at the population level. So bad leader takes the organization to the worst outcome.
The worst possible.
Then, yeah, but the really good leaders take them to higher levels. So mean-wise performs better. Variance-wise, we're playing a more risky lottery if we go for hierarchical structures.
Yeah, that's very true. In expectation, it's better, but we never know until after the fact which one we had, right? So So, but I definitely would not recommend based on these results that you systematically appoint average people on top. No, we still do everything else we normally do. But our point simply is that you don't need all of those for there to be an advantage. It can come purely from the topography itself. Okay. All right. Now, I want to do two things before we break. So first is Ekin is actually going to share with you the code that will help you to replicate these results from this paper, if you like. Okay. We want more people to try and play with this and see what they can come up with. We have made a couple of changes to the code. The most important change is we've added the top row. Okay. We now added a parameter which allows us to tune the alignment in the payoffs between the actors. In the baseline model, all actors' payoffs are aligned because they were all in the same task environment. Okay. Now what we do is we allow for each agent to be playing in their own bandit, essentially, their own set of arms. And the correlation between their payoffs across actors is tuned by the parameter alpha. When it is 0, these are like randomly different from each other. When it's 1, they're all playing in exactly the same task environment. So the results in our paper are driven from alpha equal to 1 in this model, right? But what you might want to think about is how the world might look different if alpha is 0, if they come from completely different task environments. And it's not always clear that it will actually make a difference. It may not. So let's take the case where chi is equal to 0 and delta 0 is equal to 1 and delta 1 is equal to 1. So whether they are aligned or not, does it make a difference? No, because all actions have the same payoff, which is 1. So alignment really doesn't matter here, right? So some of these cases will matter, will be different because of the alignment parameters, some will not. So you can try and do the thought experiment for yourself on where it will and where it will not matter, okay? I think a good use of the remaining time for today is, why don't we share the code with you? So Ekin, if you can just email the class, or maybe put it on the LMS or something.
It's on LMS at the moment. If you would like to,
okay,
look up the. Yeah.
Okay. Can you also just project it on the screen for a second?
Yes, sure.
So I want to show you how you could start experimenting with this, and then I want to close by making some closing remarks about the different kinds of models we've seen today.
This is fun.
What idea are you using? This looks quite awful, actually.
This is sublime. I like it. It's colorful.
Yeah. Okay. I prefer
this is the number. This is what you will find, the clean version.
Okay. So have you already incorporated number into this or not?
No, for class, no.
Okay. We'll see that next time. Actually, what we might do is create like a short video where you can just record a 10-minute tutorial on how to take a standard simulation model and then use number packages to make it faster.
Yeah.
Yeah. Okay. All right.
I can also briefly mention it's really addition of one line, but yeah, I'll make a tutorial later.
Oh, I think it'd be interesting to hear how it works. So yeah, how to make it work, yes, but like how is it able to do it faster would be useful to know.
Okay. Yeah.
All right. Okay. So the code is with you. I'm just going to point out a couple of things for you to play with in particular. So if you scroll down to the parameters at the top, let's go up to the top.
To the parameters. Sorry.
Yeah, to the parameters. Yeah.
Here it is.
Okay, there you go. So you can see there's a stack of parameters at the agent level, which is tau is exactly tau, phi is phi, w is the influence in the degrowth averaging, right? Alpha is the new parameter, which is the alignment between the payoffs for different actors in the system. So effectively, what's in the paper was all derived with alpha equal to 1. Okay. Task environment parameters are delta 0, delta 1. I don't know why they're called delta 1 and delta 2, but they correspond to delta 0 and delta 1. I won't change it here because it's going to affect all the code. Chi is written as C in the model, and in the paper you are seeing results with C 0.5 and 1. We now allow you to even make the C negative. Okay, so the third experiment I would like you to do once you've understood the code is first ask yourself, what would change if alignment went from being 1 to being 0? First question. And if the chi factor went from being positive to negative. And obviously it's a 2 by 2, right? So you can have alignment changing from 0 to 1 and chi changing from 0 to 1 and see what would it change in terms of our results. So this is the exercise that I think you might enjoy doing. And obviously then think about what is the implication of that for what's actually happening in the real world. So what are we capturing through these kind of situations, right? So misaligned alpha is probably obvious, incentive conflict, okay? What does a negative chi mean? What kind of a situation is a negative chi? In the model, we've been using positive chi, right? Where you were being penalized if you did not converge. So what does a negative chi do? Anyone?
A kind of competition that if you're taking a different position, then it's better for you.
So it's like congestion, right? It's like a congestion penalty. So if you wanted to differentiate or if you wanted to locate in a place others from different from others or strategically look different in some way, then negative chi's would do that. Okay, so some kind of substitution effect. So the same basic question at the broad level is, if you tweak these two parameters, how would the forces of bottom-up convergence and top-down convergence come together? Exactly as we did in the main analysis, we will just do it with these parameters. All right, so I leave that for you to play with as an exercise. You now have the code and you should be able to have some fun once you have it up and running. So let me close by making a couple of general statements about this class of models and what we've been talking about today. So what we've done really over 3 sessions is we went from single actor models, that was session 1, the unitary actor case. And then we expanded it to multiple actors in both session 2 with 2 and session 3 now is n is infinite, right? You could put any number. The only constraint now is computational power. I do want to point out that there are really 2 different paths to go from single actor to multiple actor, and they result in quite different models. On the left is a system where even though the system has multiple actors, in the end, they take a unified action. The entire system collectively takes one action. This is Henning's model. It's a committee, right? So to put it bluntly, what is on the left here is a committee. So on the left is a committee structure, whereas on the right, what you have is like a team, where every actor is taking an action that has a direct impact on the task environment. Okay, so the feedback the organization gets is a joint function of the actions of every member directly in the task environment, not through some aggregation function. Whereas on the left, the entire aggregation happens inside the organization, one action emerges, and the environment produces feedback on that. Okay. Now on the left, of course, you can have more or less centralized systems. So you could have voting, which is what Henning had, or you could have like a boss, a committee chairman or chairwoman who gathers all the information from everybody and then makes a final decision, right? But in both cases, it's a single actor, a single action in the end. So that's why these are called unified action distributed information systems. Whereas on the right, what we are looking at is a case where every actor is taking their own action in the task environment. So Fang et al. Is on the right. Pidzunka et al. Is on the left, right? Kochak et al. Is on the right. Okay. Leventhal 97 is on the left. Okay. In fact, it's on the top. It's a unified actor model. So these different models kind of sit in different places in this task environment. So that should give you like a mental map of the different kinds of models that we've been talking about here. So under the unified action model, the task environment parameters we really focus on is just search difficulty, right? We don't care about coordination because it's a single actor. So there is no point in studying coordination between actors since it's a single actor. The decision rights in the group could be centralized, where everybody is lobbying one chairperson, or it could be decentralized, which could be consensus or voting or some form like that, right? The structure of influence within the group could be symmetric or asymmetric. And some of the key results we already have here. Ignore the point, the first, in fact, ignore all of them because you haven't seen that literature yet. But each of these are kind of well-known results in systems of the kind you see in the first column. In the second column, you have distributed action models where the 2 task environment parameters are search difficulty, in our model delta, and gains from coordination, which is chi. When chi is 0, you have a parallel search world. When chi is 1, you have coupled search world. Okay. The decision rights by definition are decentralized because everybody is acting. The influence structure can be symmetric or asymmetric like in our model. And the results that we see there is for parallel search, we have the Fang et al. Result, which is optimal clustering. right? And for coupled search, the benefit of asymmetry. That's the advantage of hierarchy under time constraints. Okay, so that's kind of a space or a map, if you like, of how to think about multi-agent models. Okay, but notice that when we went from 1 to 2, we encountered a significant jump in complexity because of the two kinds of interaction. When you go from 2 to n, the only real tricks you need to know is use networks and then how to construct super neighbors. That's it, right? And I guess the third trick is to use a separate network for dependence and one for influence. So as long as you have these 3 tricks in your toolbox, you're done, right? What we did in our model is literally just applying these 3 tricks to take what we know from individual and dyadic learning and then scale it up to the organization level. Okay, that's it. So let's stop there and see if there are any questions or comments based on the content we've covered today.
So based on what you described about your paper, like have you started to also look at like how would a flat team differ? Like is it possible to have different types of flat teams or different structures of flat teams, or is it just one thing as of now that everybody's sharing beliefs with each other?
So the variations we have explored are things like random graphs, where the density of the flat team is not 100%. But the key property of a flat team is symmetric ties.
Okay.
Right? But are you thinking of something like with clustering and things like that?
No, as in I'm just thinking from a context perspective, like if a flat team where 5 people are functionally doing different things, but are at the same level, that would look somewhat different from a flat team where there is like somebody like a product manager who's owner of a product, but then necessarily it doesn't have like the influence over the other 5 people who might be doing different things. So that kind of flat team would be different from the first kind of flat team. And then
so we could think about that by changing the dependency structure among the actors. Right? So in fact, an interesting exercise, very easily doable with this model, which we haven't systematically done, is to study the extent to which the overlap between the influence and the dependence structure is good or bad for the system. Right? Do you want the influence structure to map one-on-one with the dependency structure, or do you not? That's really the question, right? So a lot of organizational design usually proceeds on the assumption we want this match to be very high. But that's in the case where you already know the dependence. When you're searching for dependence, is it good to have overlap or not? That's the question, right? So I think it's very answerable with this framework. We haven't answered it yet, but I think it's easy to answer.
On top of that, I want to say, so far we always model influence across all actions at every time step. So I think not only the overlap, I tried to think about this a little bit, but I couldn't come to a conclusion. But you may want to have overlap, but then on only some actions. And then, you know, maybe you want to have overlap on all the actions that are taken, and then complete, you know, orthogonality or whatever you want to call it on all the other actions that are not taken, or something like this. So there's some things to explore. It's really, it's an interesting question there to follow.
So that could be thought of, what Ekin just said, could be thought of as an action-specific chi. Okay, so right now our chi is kind of it's common to all actions, but imagine for some actions, it doesn't matter if everybody else is taking the same compatible actions or not. For others, it is. There's also a little bit of a technical detour, which I didn't want to get into, which is in our model, we set it up as if this action space is common to everybody. And the reason for doing that is because we want them to be able to exchange beliefs about their actions. But you can easily reinterpret the model as everybody's action space is different, but the action numbers refer to compatible actions. So your action space action 1 and my action space action 1 are different, but because they're both numbered 1, these are the compatible actions, right? So you can think about this also as a model of division of labor with some kind of dependency structure, but you need some system for them to be able to talk, right? If your action space is different from mine, then any belief I convey to you has no meaning. So we have to have some way of linking our actions to be able to convey beliefs about those actions. So that's just a convenience assumption for us that they are having the same index numbers. Okay, so there are 2 particular directions I want to mention in addition to the overlap between influence and dependency. One is to think about how you can use our model to study diffusion. I think you can. You can strip away like the entire chi infrastructure, set chi equal to 0, and use the network just to study diffusion offline. Second, how would you use our model to study bandwagon effects? So now you can take the entire influence structure out of the story and just use chi, right? And you can see whether people converge to one action or not based on the effect of chi. So I think the platform is super general. It can be used for opinion dynamics, for diffusion, for bandwagon effects, for single learning, parallel search, coupled learning. So it's really like a platform model. It does many, many things. So you might want to try and explore some of these alternatives and see how far you go with those. Okay, let's stop there. Sangyun, do you want to add something? You've been very silent today. Ekin's been talking twice for both of you.
I think it was easy to follow.
Okay, nothing to add then. All right, so you have like a fairly long break between now and the next class, right? The next session is on almost a month away from now. So there's like a stack of things to do now, okay? So here's my recommendation. What I think is essential that everybody does as in the group is to try and replicate one of the 3 papers that you have received, okay? That's, I think, essential. If you still have time after that, then I would say try and play with these models, do something on top of them. This is purely optional. I hope some of you will take the challenge and do it. It's not essential, but the replication is essential. What I do want, in addition to the replication for class next time, is for each of you to come with a single slide or maybe 2 slides outlining one idea, okay, that you might want to study in organizational learning using the concepts that we've covered. So to spark your imagination, I've given you 2 papers. One is by Linda Argoti and Sankili and the third person, review paper. And the other is in Journal of Management, again by 3 authors on organizational adaptation. Both are literature reviews. And the nice thing about both is they both show you what's been done and also point to what's not been done. So it's a great place for you to start to think about, okay, so if I wanted to tackle something that hasn't been done, how would I do it in a way that uses some of the models that we've talked about in the class? Okay. So in addition to your replication exercise, which is a group thing, on an individual basis, it would be great if you can bring in your ideas in 1 or 2 slides, and we'll try to get through as many of them as we can in class. I think that'd be a useful way to close the class. The theme for next time is also kind of a bit unorthodox, but it's also a theme that I wanted to educate myself on. That's why I created a session. We are going to explore the similarities and differences between machine learning and organization learning. At a very core level, they are very similar. I've already said this, right? Both learn from prediction error. But of course, there are big differences in the psychology and the sociology of how groups learn from how algorithms learn. But I found a set of papers which are quite interesting, which talk about social learning by artificial agents. Okay, these are really like multiple reinforcement learning agents learning to play a game together or do a task in an environment. And even if we don't end up adopting those models, and I can see good reasons why we don't, it's helpful to think of them as a benchmark. Okay? They might teach us more about how we should be modeling social systems just by studying those kind of systems and their limits and constraints. So that's the agenda for next time. Okay.